Now that we've talked about logarithmic and exponential functions and have seen some applications with them, we will move on to talking about calculus involving those functions, which of course starts with the ability to take derivatives of them. I'm not going to derive the very first rule I'm going to give you, but the derivative of e to the x is kind of what makes it one of the nicest functions to study in calculus, because its derivative is simply itself. Okay, so you can think of e to the x as being a very egoistic function because it likes itself so much, its derivative is simply itself. This is not quite the case with the exponential functions of different base. The derivative of that here will also be itself, but then followed by the ln of the base. Notice that it's actually kind of the same here. This is followed by ln e, but ln e is 1. For a quick example here, let's take a look at how one would take a derivative of, let's say, e to power 3x. Okay, so remember that all of the differentiation rules we've covered up until now will still apply no matter what the function you're taking the derivative of is. So if you have a product, you will have to apply the product rule. If you have a quotient, the quotient rule. If you have an inside and an outside function, you will have to apply a chain rule. Okay, so in this case, this is exactly where we see the chain rule first applied to exponential functions. We have not just e to the x, but rather e to some other power, 3x. So here we have to pause for a minute and think about what is the inside and what is the outside function. So this function e is actually the outside, and my power in this case is the inside function. Remember the chain rule? The chain rule says to first take a derivative of the outside function, keeping the inside as it was. So the outside function is e to some power, which has the derivative as itself. So the outside derivative is simply e to power 3x, followed by the derivative of the inside. The inside here is 3x. The derivative of 3x is simply 3. Okay, you will do more examples in class, but let me just do one other one here. What if we were to take a derivative of, let's say, e to power x squared plus 1? Same idea. Now we have the outside function is still e, the inside is still the power. So I'm going to take the derivative of the outside first and keep the inside intact. So the outside function is e, its derivative is itself. So e to whatever power it happened to be, x squared plus 1, followed by the derivative of the inside, 2x. Okay? Now this is for the derivatives of the exponential functions. What about logarithmic ones? So the function, a logarithmic one, let's take a look at the one with base e, because again, that's going to be the one that we mostly work with anyways. So this is the function whose derivative I'm after. So if it's y equals ln x, it's y prime that I am seeking. Now, we already know how to take derivatives of exponential functions. So as the first step, it would make sense to transform this function into an exponential function whose derivative we already know how to take, and then apply implicit differentiation. Okay, so as the very first step, I'm going to rewrite that as the exponential function. There's a couple of ways to think about it. I know you guys have practiced turning exponentials into logarithms and back. So turning this into an exponential function, you should get e to power y is equal to x. Now, once again, I already know how to take derivatives of exponential functions, so I can simply apply implicit differentiation to this entire equation. Okay, so we will take a derivative of that as is. What do we get on the left-hand side? On the left-hand side, we have e to power something. So the derivative here is itself, except for the inside of it is not just x, but y, which is a function of x, which means that, as implicit differentiation suggests, I should follow up by the derivative of y, which is y prime. It's implicit differentiation. I don't know what y prime is. I'm just going to keep it as a packaged deal here. And then equals to the derivative of the right-hand side. The derivative of x is just 1, so I have just 1. Now remember, I'm after y prime, so I'm going to solve this equation for y prime. What do I get? I get 1 over e to power y. And this is allegedly my answer. So the derivative of ln x is 1 over e to power y. Preferably, my answer will only contain x's. So I'm wondering if I can replace this y with some x, with the function of x that it corresponds to. And remember that y itself is just ln x. So if I plug it back into here, what am I going to get? I'm going to have 1 over e to power ln of x. Exponentials and logarithms are inverses of each other. So I'm going to get simply 1 over x. Excellent. So that means that the derivative of ln of x is just 1 over x. Okay? And once again, all of the same differentiation rules that we have seen before still apply to this function here. So for example, ln of, let's say, 5x, the derivative of that. So here, once again, you have to think about what is the outside function and what is the inside function, because clearly the inside is not just x anymore. In this case, logarithm is the outside function. It's a logarithm of something. So this guy is the outside function, and whatever lives inside of it is then the inside function. Okay, so as per chain rule, I first take a derivative of the outside, which is ln of something, and the derivative of ln of x is just 1 over the inside. Keeping the inside intact, the derivative of ln of 5x is first of all 1 over 5x, 1 over all of the inside, times the derivative of the inside. The inside is 5x, the derivative of it is just 5. Okay, and that's your answer here. Just for a little bit of extra practice, maybe try taking the derivative of x times ln x, just to remind yourself that all of the differentiation rules will be inherited for all the functions. So here, it's first of all a product, which means that we will have to apply a product rule, and then whatever other derivatives that we need to take. Equipped with the now newfound ability to take derivatives of exponential and logarithmic functions, we can move on to talk about how to do calculus using those functions. So how to find global or local maximum minimum, inflection points, sketch the functions, and so on. Our first application is that of cardiac output, which is the volume of blood pumped out by the heart per unit time, or sometimes measured as per heartbeat. One of the most common techniques to actually measure the cardiac output, and therefore how well your heart actually pumps blood, is through thermodilution. Believe it or not, this is a minimally invasive procedure that can be done bedside, but it involves inserting a catheter into the heart, and then as it goes through the right atrium, releasing a small amount of cold dextrose or saline solution, and then tracking how the temperature of it changes on heart's exit. Okay, so here at the exit of the pulmonary artery. Okay, so the cold temperature of the actual solution warms up as it travels through the heart, and the faster its temperature returns to normal, the better your cardiac output actually is, because the faster your heart managed to get that solution out. The reason that this is preferred by many is because, again, it's minimally invasive, and it can also be repeated. So normally there are a couple of injections that happen, and an average of the cardiac output among different measurements is taken. The other nice thing is that because this is all automated, we actually know what a normal temperature variation curve in this process looks like, and it can be modeled closely by a function like this. So here we have 0.2 t squared e to the minus t. This shows the temperature in degrees Celsius, and t is measured in seconds. So this will tell us what the temperature is seconds after the injection of the cold solution into the heart. We would like to find, classify, and interpret critical points of this function, as well as to sketch it, which means that we have to pull out all of our calculus arsenal, take the first derivative, find critical points, take the second derivative, find inflection points, talk about the intervals of increase, decrease, as well as concavity, and then put all of this information onto the graph. So let's first take a derivative. Let me rewrite the function so I can analyze it a little bit closer before actually differentiating. So first and foremost, notice that this is 0.2 t squared times e to the negative t, which means that before anything else, this is a product, and therefore we will have to apply the product rule. Okay, so remembering the product rule, I'm going to have the derivative of the first function, which here I'm going to consider to be 0.2t squared. So the derivative of that is 0.2 times 2t, and then we leave the second function alone, plus we leave the first piece and take a derivative of the second function. So now I have to take a derivative of e to the negative t, which is itself, times the derivative of its inside. Its inside is minus t, so the derivative of that is minus 1. Now, in order for me to better see what is actually going on here, I'm going to try to simplify this expression by factoring things out. So I'm going to look at both of these terms and see what it is that they have in common that I can take outside of the brackets. Clearly, they have a 0.2 in common. There's also a factor of t here and here. There's actually t squared, so I'll be able to take one of them out. And there's also e to the negative t in both terms. So I can take out this entire factor, and then what I will have left, well, let's say I took out 0.2, I will have 2 left here. I took out the t and I took out e to the negative t. So from the first factor, from the first summand, I only have 2 left, and from the second one, we took out 0.2, 1 of t's, e to the negative t. I will have minus 1 remaining, and I will also have a little factor of t there. So altogether, there will be 2 minus t left in the brackets. Okay, sorry. So for the critical points here, again, remember that I need to set my derivative to be 0 or does not exist. Factoring is particularly helpful for solving something to be 0 because factoring turns anything into a product, and a product is only 0 if one of the factors is 0. So here I simply need to now analyze this entire expression factor by factor. 0.2 can never be 0. T is 0 when t is 0. E to the negative t, which is our next term, is never going to be 0. No matter what power you raise e to, it's always going to give you a positive result. And this is one of the nicest things about analyzing exponential functions. You can think of that in terms of the graph, or you can actually think about that in terms of raising something to the power. No matter what function I pick, what number I pick, if I raise e to that number, the result will always be positive. So e to the negative t is never 0, so that produces no solutions. And this bracket, 2 minus t, is equal to 0 when t is equal to 2. So those will be my 2 critical points, 0 and 2. From this case, and then I also need to consider, when does the derivative not exist? Well, let's take a look at the actual derivative. This is it. Are there any numbers that I will not be able to plug in? Well, not really. This is a power, so I can plug in anything, and the rest of it is polynomial, so I can plug in anything again. So this has no solutions. Okay, so I only have 2 critical points, and I'm going to analyze the first derivative by drawing a number line, putting both of those points on. Now, of course, notice that t being measured in seconds after the injection means that t cannot be negative. I'm going to include this in my analysis just to get a fuller picture of what the function looks like mathematically. Now I can plug in all the different numbers in these intervals. So if I plug in something negative, I'm going to be plugging it into the derivative. Let's see what happens. 0.2 is positive. If I plug in a negative number, t will be negative. E to the negative t will be positive no matter what. And then this will be a negative number here, which will become positive with a minus in the front. So altogether, this contribution will become negative. This contribution will stay positive. So I have negative altogether. You can use a similar logic for all the other intervals, or if you prefer, you can grab a calculator and just actually plug in a number in. I find that thinking it through is actually faster in the end, because for example, again, here, if I plug in a 1 into this entire expression, this whole part is positive. Because once again, I don't even need to bother plugging anything into e to some power. That will always remain positive. And 0.2 times 1 is positive. 2 minus 1 is also positive. Positive times a positive gives me a positive. The last one will be negative. And thinking in terms of the function, that means that the function was first decreasing and then increasing and then decreasing again, producing a local minimum at 0 and a local maximum at 2. Okay? So this is the situation for the local extrema, which is what the first derivative analysis will give us. Local minimum at 0 is not surprising. That's when the injection first happens. But let's try to think about what does it mean to have a local maximum at 2? Well, that requires thinking back in what the T is measured in, and that is measured in degrees below normal temperature. So local maximum being at 2 means in 2 seconds, we have the greatest difference between the measured temperature and the normal temperature. That's when the cooling down effect is the most noticeable. So in 2 seconds after the injection, the temperature drops the most. And this is how one can interpret the first derivative in this case. Let's now take a look at the second derivative and its analysis in order to determine potential inflection points and intervals of concavity. So if you carefully take the second derivative, you should get an expression that looks like this. Once factored out, 0.2 e to the negative t, t squared minus 4t plus 2. Once again, you factor it out in order to be able to better analyze when it's actually equal to 0. So our potential inflection points are going to be when the second derivative is either equal to 0 or does not exist. Once again, going through this, the second derivative being 0 means one of the factors has to be 0. 0.2 is never 0. E to the negative t, once again, is never actually 0 or negative, which means that we only need to solve for this quadratic to be 0. Now, a lot of times you are able to find nice solutions to quadratic equations. This is not one of those cases. In this case, you will have to apply a quadratic formula, and it will produce two slightly ugly solutions, 2 plus or minus square root of 2, which are approximately equal to 0.58 and 3.41. Okay, so those are our potential inflection points from this case. And then the second derivative does not exist. Once again, we have to look at our second derivative here. We notice that this part is just a polynomial, so you can plug in any number, and you can, of course, compute an exponential function at any number x, or t in this case, sorry. So this produces no solutions. Okay, now let's actually do the second derivative analysis on it here. So my two potential inflection points are 0.58, 3.41, and once again, you don't have to really consider the negative numbers because t here represents time and therefore cannot be negative, but it does give a better, fuller mathematical picture. So if we pick a number in this region, we plug it into the second derivative here, and we have to figure out whether it's going to be positive or negative. Once again, you can use your calculator, or you can sort of justify it out. This entire part will always be positive no matter what you plug in. So we really only have to figure out whether this quadratic is positive or negative for the chosen numbers. It's going to be positive and then negative and then positive, which means that the function is concave up and then concave down and then concave up. Because the concavity actually changes at these points, we will have an inflection point at each one of those spots because there are also actual points on the function. Excellent. This is our first and second derivative analysis. Remember that we want to sketch the graph. We also want to find things like x and y intercepts and asymptotes. I'm going to leave the x and y intercepts to you. You should only get one, and that will be at the origin. But for the asymptotes, for the vertical asymptote, there is no number that you can plug into the function to make it go to infinity except for infinity. So there's no vertical asymptotes. And for horizontal asymptotes, remember that we always have to compute the limit as the variable goes to infinity of our actual function. So what happens in this case, let us rewrite e to the negative t as the actual reciprocal with the positive power, as it might be slightly easier to analyze. Okay, so I have an expression that looks like this. If I plug in what the limit tells me to compute this function at, I'm going to get infinity over infinity. This is actually one of the indeterminate forms where so-called L'Hopital's rule will be quite useful. We do not cover L'Hopital's rule in this course. It is useful for functions like these, but there's another type of analysis that we can do here in order to figure out this limit. It is infinity over infinity, but notice that the top infinity is formed by a polynomial function, while the bottom infinity is formed by an exponential function. Exponential functions grow quite a bit faster than polynomials, which means that the infinity on the bottom will be a much larger infinity. So you're dividing a number by a much larger number, which will make the limit go to 0. With all of this in mind, let's try to put all of this information onto our graph. Okay, so what are some of the useful points where you would like to have both x and y coordinates? Those include your critical points, as well as your inflection points. So we would like to compute t at 0 and at 2, as those were our local minimum and local maximum. I'd also like to know what t is at both of the inflection points, so that we can sketch those on. Please take a minute here and try to put all the information that we found back onto the graph, keeping in mind the intervals of increase, decrease, as well as concavity. Okay, and when you come back, I will show you what the graph looks like. This is what a graph should look like. You notice the local minimum at 0, local maximum at 2, concave up behavior at the beginning, switching to concave down between the two inflection points, coming back to concave up again. Whenever you have a problem situated in context, it's always a good idea to check whether your graph or your conclusions make sense within the actual problem. So remember that the temperature is measured in degrees below normal, which means that at 2, for our local maximum, that's when the temperature dropped the most. And then notice that afterwards it converges towards 0. 0 degrees below normal means that it converges back to normal, which makes sense. After a certain amount of time, the temperature in the heart will come back to normal. Especially in this particular case, it's not going to take that long because the amount of solution injected is usually very small. Same for in the beginning, it increases, so the temperature goes away from normal and then comes back to it. The situation, the graph seems to make sense in the situation, so this is a good common sense check, just to make sure that some silly arithmetic mistake did not lead you to a completely misguided graph.
Before we proceed with further applications, let's take some time to compute derivatives of more complicated exponential and logarithmic functions. Nothing here is new, so please pause the video and try these out for yourself before coming back to see how we can get through these together. So first up, we have e to the 5x. The question to ask yourself is this a function that is composed of other functions? And if so, what is the inside and what is the outside of it? So the inside function here will be my 5x, because overall we can say that this entire function is e to some power, and then insert that power into the actual consideration. And the outside function here is going to be the function e itself. In fact, with exponentials and logarithms, it is always fairly straightforward because the exponential or the logarithm itself is going to be your outside function. So once we have determined this, we simply are going to follow the chain rule that we have established in lectures previously. So according to the chain rule, I first have to take a derivative of the outside function. Remember that e, exponential egoistic function, the derivative of it is simply itself. So I am simply going to write the exact same expression, and this constitutes the derivative of my outside function. And then I have to follow up by the derivative of the inside. The inside is 5x, so its derivative is going to be simply 5. And once I have done this, I am, in fact, done taking the derivative of this entire expression. Moving on to the next one, e to the power x squared minus 3. The analysis here is extremely similar. The outside function is the exponential, the inside function is x squared minus 3. So according to my chain rule, I'm going to have very similar calculations. So for part B here, I'm going to have the derivative of the outside function as itself, because it is in fact the exponential, followed by the derivative of the inside. The inside function now is x squared minus 3, so its derivative is going to be 2x. Next up, we have x squared times e to the negative x. And the first thing to notice here is that I actually have two different functions, and they're put together using a product. If I have a product, my first idea to apply is, of course, the product rule. So according to the product rule, I have to take a derivative of the first function and follow it up by the second function, plus I leave the first function alone and I take a derivative of the second function. Once we have written it out like that, we can go ahead and actually take those derivatives. So the derivative of x squared is 2x, and the derivative of e to the negative x, we gotta be a little bit more careful because now this is actually of the same form as the first two examples here. It is e to some power, but that some power is not just x, it's negative x. So I have to apply chain rule here. Therefore, the derivative of e to the minus x is itself times the derivative of the inside. The inside is minus x, so its derivative is simply minus 1. You will notice that as you do more and more of these examples, the derivative of e to the negative x is just minus e to the minus x. And that is just a shorthand rule that you can remember. Next up, x times ln x, and we're going to be in a very similar situation to the example before. I once again have a product here, and therefore I will once again apply the product rule. So if you haven't paused the video yet to try these out for yourself, now is the time to do so. So according to the product rule, I take a derivative of the first function, which will be 1, times the second function, which is ln x, plus I leave the first function alone, so I can leave x alone, and take a derivative of the second function. The derivative of ln x is simply 1 over x. I'm done taking derivatives, and here I'm just doing this for practice, and I'm not asked to simplify or work with my derivatives any further, so I'm going to leave this expression as is. But if you wish, of course, you can simplify this function quite a bit to, if you're planning on working on this, this is something that you certainly would like to do. Next up, we have x divided by e to the x. And here we have options as to what to apply. We can apply the quotient rule as the function is written as a quotient, or I can rewrite this function as a product and apply the product rule. So I can rewrite this as a product as x times e to the negative x, and then apply product rule to it. I'm going to leave this as an extra example for you to try both of these for yourself. I do encourage you to try both just to see which one you actually prefer, and to also solidify in your mind the fact that when you see a function, there's usually more than one way to take its derivative. So take a moment, look at the function first, simplify or modify it as you see fit, and then proceed to actually take a derivative. Next up, we have ln of cube root of x. And here we once again have more than one possible way to actually apply the differentiation. First of all, we can simplify before we differentiate. Normally, that actually shortens the process, so we can do that. If you remember, the logarithmic rules state that if I have ln of something to the power, that power can come to be in front of the ln. So here, the power is 1/3. So I can rewrite this as ln of x to power 1/3. 1/3 can come in front of the ln, and overall I will have that this is the same function as 1/3 ln of x. And now taking the derivative of that is going to be very straightforward. I leave the constant alone, and I take a derivative of the non-constant part of the function. Ln x, the derivative of ln x is simply 1 over x, and I'm done. If I did not simplify this function first, and I decided to take a derivative of it as is, what I would have to do is apply the chain rule. Ln, logarithmic function, is going to be my outside function, and cube root of x is going to be my inside function. So overall, if I was taking the derivative of this directly, I would have to first take the derivative of the outside function. Outside function is the logarithm. The derivative of a logarithm is 1 over whatever is on the inside. So 1 over cube root of x, followed by the derivative of the inside. So the derivative of the cube root of x. So because this is not uber easy, I'm going to actually write it out as a derivative first before taking it. And now I can go ahead and actually take the derivative of that. The derivative of cube root of x is the derivative of x to power 1/3. So the power will come down, and I will subtract 1 from the power. And this is the expression I end up with. If I simplify this, I will notice that it's actually equivalent to this expression here as well. But I've done both methods just to illustrate to you that simplifying first results in a much shorter differentiation process, whereas not bothering to simplify gets you to go through complicated differentiation, including the chain rule, as well as simplifications that are harder than the original ones done in the first place. So if possible, simplify first and then differentiate. And that is the same idea as I leave you with for this last example here. Try to simplify this expression first and then apply the appropriate differentiation rules. So simplify, then differentiate, and then see what it is that you end up with. Now back to applications, let's consider the growth and decay model given by a simple equation that we learned about last time. So this is an entire family of function depending on the values of p naught and k, and we, in this example, are asked to consider a specific example of 100e to power 0.12t, where that model describes the number of people infected with the flu at particular time t. And then we're asked two different questions about it. How fast is the infected population growing right at the beginning of the epidemic? And how many people have the flu in 1 month? Before we get to these two questions, let's actually take a look at our model itself. So we are given the model with concrete values for constants. So let's try to think about what these constants describe and how they actually illustrate the situation. So first of all, of course, 100 corresponds to P naught, which means that at the beginning of this flu season, there were 100 people that were infected, and that is where we're beginning our countdown. And the value for the growth constant being positive indicates that the flu is indeed spreading. It is spreading unboundedly. So here we're not talking about recovery rates. We're simply looking at the number of people infected throughout the actual season. Now, this number can be interpreted in yet another way, and that is, we can think of that as, in fact, a percentage. At any instant, the disease is infecting 12% of the current population. And this is actually going to raise some important small details in the later analysis. So let's write it down and let's let it sit with us for a minute. So at any instant, the disease is infecting 12% of population. So the moment the population changes, the percentage of it that is being infected changes with it. It's not a fixed number. It doesn't mean that there are 12 people infected, for example, every single month. It means that whatever the population is, it's going to be 12% of that number. So now the first part is asking how fast is the infected population growing at time 0? How fast indicates that we need to compute the derivative at time 0 indicates that we need to, in fact, compute it at time equals 0. So before we can compute the derivative at time 0, we need to compute the derivative for any given value t. So that means I have to take a derivative of this function. Following the rules that we have just discussed, I'm going to leave the constant alone. The derivative of the exponential function is itself, followed by the derivative of the inside, which is 0.12. So now, if I compute this value at 0, I'm going to plug 0 in for t. The entire exponent is going to turn into 0, which will turn the entire expression involving e into 1. So I'm going to end up with 100 times 0.12, which is 12. Now, what are the units of this particular expression or this particular function? Remember that maybe rewriting it in a different notation will help with units. dp by dt. The p, the population, is measured in the number of people, and the time is measured in months. So I will have myself 12 people per month. So that means that right at the beginning of the flu, there are 12 people per month that are being infected. Now, the next question asks, how many people have the flu in 1 month? So, given what we have just computed, we can actually use this to give us some intuition as to what number we expect the model to produce. We started with 100 people, and right at the beginning, the flu is spreading at 12 people per month. So, we can expect that in 1 month, we will have 100 people that we started with, plus the 12 new people that got infected. Now, this, in fact, isn't the exact value because we're not using our model directly, but rather reasoning about it. So it's actually going to give us an approximation. So 100 people at the beginning or at the start plus the 12 new people in first month will give us that we are expecting 112 people by the end of the first month. The exact value, however, we will calculate by using the model directly. So I'm going to plug t equals 1 for months into the expression. So in a month, my model will give me that I have 100 times e to the power 0.12 times 1 month. And if we calculate that, it will actually give us 113 people. So now let's pause here and think about the small discrepancy. Our intuition based on the original calculations suggests 112 people. Our model is giving us 113. So how come there's a small difference between numbers? And it all comes out to exactly what we have noticed right at the beginning. At any instant, the disease is infecting 12% of the current population. The moment the number of people infected grows, the actual number of infected people grows with it. So here, it went from 100 to 112 within a month, which means at some point it was 105 people, and we were supposed to be infecting 12% of this new total of 105 people. This continuous compounding is actually what is attributing to our model producing a higher number than what we might expect. Let's take a look at what the graph will tell us about the situation and how we can reason this out in a visual way. So if we actually just sketch our model, it is an exponential. It starts at 100. I'm not going to draw to scale. I'm going to draw to illustrate. So let's say it's something like this. Goes with time and the number of people infected. So what I have in 1 month is my model told me that I have 113 people that are infected, again, according to my model exactly. So where can I find this 12 people per month rate? Notice that this was the derivative at 0. The derivative on the graph is the slope of a tangent line, and my tangent line was constructed at 0. So that means that what we did here is we constructed ourselves a tangent line at 0, and then we looked at the value of that tangent line in 1 month. And this is exactly what produced a smaller number at 112. As I said, the graph is not to scale, it's for illustrative purposes. But we can see clearly that here the tangent line will lie below the curve, and therefore our approximation or intuition will produce a smaller number than we actually see the model predict. It's important to remember this because, again, this compounding continuous behavior of the function will always get a little bit, will always mess with our intuition a little bit. So it's important to remember the differences between plugging into the exact model and doing mental calculations with the rate of change constructed at a previous point in time. Our next application here has to deal with thermic effect of food. It is well known that a metabolic rate of a person goes up after a meal, and there is some time that passes before your metabolic rate returns to resting rate of your general average norm. Now, what actually happens, of course, is the fact that as you consume food, your body takes energy to digest it. So not only are the number of calories consumed not the number of calories that have been digested, it actually takes about 5 to 10% of the food's total energetic amount for the body to digest that food. So what we're going to be interested in is analyzing the function in terms of this thermic effect. So how long does it take for your body to return to the resting metabolic rate after a meal? And we have data from a study that consisted of 131 thermic effect of food tests taken from a wide range of subjects in terms of gender, age, race, and so on. And the mathematical model that was produced is this particular model, where T, appearing in a few spots here, stands for the number of hours that have elapsed since eating a meal. we are going to analyze the behavior of this function. So first of all, we're asked to compute the average rate of change of this TEF function during the first hour after eating. It is also important to remember that the calories are here are measured in kilojoules and the time is going to be measured in hours. So the average rate of change, remember, it's just the slope of a secant line or the rise over run between the 2 points where we're interested in terms of being the beginning and the end. So all I have to do here, the first hour, is compute the difference in the actual TEF numbers divided by the total number of hours elapsed, which is 1. So if I plug in 1 into here and then I plug in 0 into here, compute the difference, I'm going to end up with the number of approximately 81.5. And of course, my units are going to be kilojoules per hour. Fantastic. So what are we going to be asked to compute next? Next up, how fast is TF changing in 30 minutes? Interpret your answer. How fast indicates that we're after the derivative. In 30 minutes means that we're after the derivative in half an hour. Remember, your units, you have to be consistent with using your units throughout. So first of all, we have to compute the derivative overall and then plug in half an hour for that. This is a great place to actually stop and once again practice your differentiation skills for the exponential functions and the various laws that you might need to apply otherwise. So pause the video, try it out, and then come back. So taking the derivative of this, I notice that the first part is a constant, so its derivative is going to be 0, and then I have to take a derivative of my second term, which happens to be, of course, a product, so I need to apply a product rule. I'm going to first take a derivative of the first term, which is 176t, so the derivative is going to be 176, and then I simply rewrite my second term, plus I leave my first term alone, and take a derivative of my second term, which being the exponential is itself, followed by the derivative of the inside. Now the inside here is always a little bit more confusing than it actually is. Notice that what I have is minus t over 1.3. I can rewrite that as minus 1 divided by 1.3 times t, and then taking the derivative of that is a little bit more obvious. I have a constant followed by t. So the derivative of this expression is simply the constant, minus 1 over 1.3. Okay, as per usual, simplifying before taking the derivative is helpful. And then I can plug in the point in time where I'm interested in actually computing this derivative, which is half an hour. So here, what the number is going to come out being is approximately 73.7, and my joules are, or my units are kilojoules per hour. And so the metabolic rate in the half an hour is going to be 73.7. The metabolic rate is going up in the first hour, half an hour after eating the food. Now let's take a look at what happens as time goes on. So of course, we're interested in determining when the function is increasing and decreasing. Increasing function means that your metabolic rate is up. Decreasing function means it's going to be coming down. And the eventual question is, when is it maximized? So when is your metabolic rate maximum after the consumption of the food? And maybe how long does it take to come back to approximately normal? So how long does it take to even out again and essentially come back to 0? So if we're interested in increasing and decreasing behavior, we are of course interested in the critical points and then the behavior of the derivative of the function. Remember that we've already computed the derivative on the previous slide, and now we simply need to set it to be 0 and not existing and actually compute the critical points. So the derivative from the previous slide was 176 e to power minus t over 1.3, and then followed up with the second portion of our product rule. So in particular, this expression. The reason I'm writing this out this way, and I'm not actually simplifying, is to show you that you don't actually need to multiply these numbers together. Rather, we're going to look at the expression as a whole. I need to figure out what the critical points are, which means I need to solve for this expression to be 0 or not existing. So let me simplify it first to see what kinds of patterns there are in it. So I notice that I have two terms that are connected with a plus. So what do the terms have in common that I can factor out? The terms have 176, both of them, so I can certainly take out 176. And the terms, both of them, have e to this power. So I can also take that entire term out. What am I going to have left? I've taken out 176 times e to the entire power. So I've taken out this entire term out. So what I have from the first term here is just 1. And then what do I have left from here? I took out 176 and I took out e to the power. So what I have left is minus t times 1 over 1.3. And now that I have it written out like this, it becomes much easier to actually solve for this expression, for example, to be 0. So when is my derivative equal to 0? Remember that the reason that having a product is convenient is because the product is only 0 if one of its parts is 0. So either this part is 0. Let me move things around so I can analyze this a little bit better. So in terms of being 0, either this is 0 or this is 0. The exponential being 0 produces no solutions. Remember what the exponential function looks like even with the negative exponent? It looks like a decay function. It will get closer and closer to 0, but it will never actually cross the axis, which means that it will never be equal to 0. So this part produces no solutions. And the second part, of course, produces the solution of t equals 1.3. And that is one of our critical points. The other case I also have to consider, when does this derivative not exist? So taking a look at my expression here, what are the values of t that I cannot plug it into a function? Well, exponential is defined for all t's, and in the brackets, I only have a linear function really. So there are no solutions to this particular case, and therefore my only critical point is the one that I found here, which is 1.3. So with that in mind, I'm going to draw myself a number line, put all of my critical points on it, which is again, just 1.3, and analyze what happens to the derivative before and after it, and then be able to conclude what happens to the function itself. The fact that I only have one critical point divides the number line into two regions. I can pick a number here and plug it into the derivative. The other thing that is really easy to analyze with derivatives that involve exponential functions is the fact that e to any power, be it positive or negative, is always positive itself. So really, the first two terms here will forever be positive, and therefore, in terms of sign, I only have to think about what happens to this bracket. If I pick a point here, for example, 0, and plug in for this bracket for t, I will notice that I end up with a positive number. 1 minus 0 is going to be positive, so my function here is positive. If I pick a number on this side, for example, 1 million, and I plug it in for t in this bracket here, I will have 1 minus a big number, so it's going to be negative. If you're more comfortable plugging the actual exact numbers into your calculator to figure out the sign of this entire expression, by all means. As I've already mentioned, for me, this creates more opportunities for mistakes, and I prefer the general analysis. Now, if the derivative is positive, it means that my function is increasing. If the derivative is negative, it means my function is decreasing. I know that this was a true critical point and not an asymptote, which means that by first derivative test, increased followed by decrease will produce a local peak and therefore a local maximum. Now, the question itself actually asked, when does the function increase and when does it decrease? The function is going to be increasing all the way up until the local maximum here, and afterwards it's going to be decreasing. The question also asked to interpret that. Well, it means that your metabolic rate goes up all the way to 1.3 hours after the meal, after which point your metabolic rate starts decreasing and eventually returns to normal. The last part on this slide here asks to find the time after the meal when the thermic effect of food is maximized. Now, if we're looking for the global maximum, we're going to remember that what we need is to consider the critical points and the endpoints. So the critical points, as we've discovered in the previous part, there's just one, 1.3. So I have that as one of the candidates for the global maximum. And in terms of the endpoints, I can think of what happens right at the beginning of the food consumption and what happens eventually. So maybe if we didn't know and didn't have real life experience, maybe one can hypothesize that after the meal, the metabolic rate is forever climbing and increasing. Let's see if plugging in these points will confirm or deny such a hypothesis. So remember that if I'm looking for global maximum, I have to collect my candidates for it, which are critical points and endpoints. And now I have to plug all of them into the function itself. What I'm looking for are the actual function values. So I'm going to compute f of 1.3. I'm going to compute f of 0. And I'm going to compute f of infinity. Now, of course, I can't compute f of infinity. I can't plug in infinity itself. So I'm going to compute the limit of my function as time goes off to infinity. So here, all I'm doing for the first two are actually plugging in numbers. And I'm going to get, in terms of numbers, 73.9 and minus 10.28. Right? Plugging in 0 is actually fairly easy. 0 is going to go here. That whole thing is going to become 0. So this is the only thing that I'm going to keep. What about computing the limit as t goes to infinity? So t becomes a very, very large number here. And we're not actually talking about that particular way of calculating these limits mathematically, but I'm going to assume that you can use your geometric intuition to reason out the fact that this entire term, when t goes to infinity, will approach 0. And so for infinity, my answer is, one again, going to be minus 10.28. So before eating, my metabolic rate was at negative 10.28. After a long time after the meal, my metabolic rate is again at minus 10.28. So this suggests to me that this is in fact my resting metabolic rate, and that is what my body needs to spend just to sustain life. Whereas obviously this number is bigger than either of these two, and this is going to be, in this case, my global maximum. Now, given all of this information together, I can compute a whole range of other things. For example, I can also run my second derivative test and figure out the inflection points and so on and so forth, and overall sketch the graph of the function. I'm going to leave the last steps for you to actually fill in, and I will give you the graph of the function to compare your sketch to. So what we're seeing here is this is my maximum, global maximum that I've discovered. So this happens at 1.3. What I can see, of course, is that at 0, I was at minus 10 and a little bit, and eventually I will approach that same number asymptotically. Confirm that this is going to be your graph following your findings. Think about how you would find concavity for such a graph, and think about what are the actual intercepts representing. For our final application in this lecture, we're going to look at aerobic rate. Aerobic rate is the rate of a person's oxygen consumption, which can be modeled by this particular function, where x is greater or equal than 10, and x is actually the age of a person in question. We are asked to simply graph this function. Now, if you're asked to graph this function, you will have to find the intervals of increase, decrease, the intervals of concavity, local maximum, local minimum, any inflection points, if there are any, asymptotes, and so on. So graphing the function isn't as easy as it sounds. It is involving all of the calculus tools that we have used before. Now, because it is all the calculus tools that we have used before, I strongly encourage you to pause this video and actually do this example all by yourself, going through finding the intercepts, finding the critical points, finding the potential inflection points, and all of the first and second derivative analysis involved before producing your own graph. I meant for this question to be an extra practice, and we would have been doing this like that in the physical class. So please don't just watch me go through the motions. I can certainly graph the function all by myself. I am more interested in you practicing your skills to do it by yourself. So starting with the intercept, just so we can put some points on the graph, let's take a look at what is the intercept of the x-axis. So if we set y to be 0, what are we going to see? Well, this entire expression is really a number times a big fraction. And remember that a fraction is only ever equal to 0 if the top of it is 0. So what I have here is that ln of x minus 2 has to be 0, which also means that ln of x has to be 2. So my intercept is going to occur when x is e squared, or approximately 7.4. What is important here to notice is that it happens before the domain of the function that I'm interested in. 7.4 is less than 10, so this is not sort of in the area of my concern. Mathematically, I can of course still graph for all of the values for x, but in terms of our application, this is not in the domain. Next up, we have to compute our critical points in order to find out what are the intervals of increase, decrease, and the potential local max and min. Now, I'm not going to go through the motions of actually computing this derivative by hand here. You can do so, or you can call on Wolfram alpha and figure out that your derivative is going to be this expression right here. So now we have to figure out when this derivative is equal to 0 and when this derivative does not exist in order to compute all of our critical points here. So once again, having the derivative as one big fraction is really beneficial, because one big fraction is only equal to 0 if the top of it is 0, which in this case means that ln of x is equal to 3, which means that x is equal to e cubed. And the derivative does not exist when the bottom of it is 0. So in this case, x is equal to 0, which is not in the domain of our consideration. So not in domain here, which means that we can exclude it from our first derivative analysis. So next up, as usual, the functions are new, but the methods are all the same. I'm going to draw my number line, and I'm going to put all of the critical points that I found on the number line. Now, there only one critical point in the domain is e cubed, so this is the only one that I'm going to include. Now, as I've said before, I'm perfectly happy working with numbers as exact and calculator-ready expressions, e cubed. If you prefer this to be an actual decimal number, by all means write it like that. It's approximately 20.8 or something along those lines. So this one critical point splits my region into two, but you have to remember that my region actually starts at 10. So I'm only interested in the numbers between 10 and e cubed and the numbers from then on. And I'm going to plug in those numbers in order to analyze what is the sign of the derivative, and then what does that mean about the behavior of the function itself. So if I plug in a number in between here, so again, this is approximately 21. If I pick a number and plug it into here, if I pick a number in this region and plug it into the derivative here, I am going to see that the derivative is going to be positive. If I pick a number after e cubed, I'm going to find that the derivative is negative, which means that my aerobic rate is increasing up until e cubed and then decreasing after, which means, of course, that at e cubed, I hit a local maximum. Now, this is my first derivative analysis. Next up is investigating what happens to the second. Now, as I said already, I'm not going to go through computing the actual derivatives here. You can do so yourself. I am simply going to write down what the second derivative actually is. So the second derivative in this case is going to be equal to this expression, minus 110 to ln of x minus 7 all over x cubed. And for the potential inflection points, I have to follow a similar analysis to the first derivative, but using the second derivative. I'm going to find when the first derivative is equal to 0 and when the second derivative does not exist. So as before, having one coherent function as a fraction is particularly useful. It's equal to 0 if the top of it is 0, and if you expand it out, you will see that that implies 2 ln of x is equal to 7, or, well, let me write this down, is equal to 7, or if we solve for x, this will give us that x is e to power 7 over 2. And the second derivative doesn't exist when the bottom is 0, which here implies x is equal to 0, which once again is not in the domain of our consideration. Now, Once again, following my second derivative analysis, I'm going to take all of my potential inflection points in the domain. So I start at 10. I put all of my potentials that I have discovered using this analysis onto my number line. And I'm going to then go through figuring out what is the second derivative sign, positive or negative, and what does that imply about the behavior of my function. So if I pick a number in here and I plug it into the second derivative, I discover that that will produce a negative result. And if I pick a number on the other side of e to 7/2 and plug it into my second derivative, I discover that this will produce a positive value as a result. So that means that before e to the 7/2, my function was concave down, and after it was concave up. Since the concavity indeed changed, that means that what I have is a true inflection point. Not a potential one anymore, but a true one. So now I have done everything that I can do in terms of computing with the first and the second derivative, finding out the intervals of increase, decrease, and so on, so I can actually proceed to sketching my graph. However, before I really think about putting things onto the graph, it might be helpful to think about what points are important and what are their y values. So on the previous slide, I've discovered that my critical point and the local maximum is e cubed, and therefore it might be useful to compute where exactly on the graph e cubed actually occurs. And here my inflection point is e to power 7/2, and so it might be useful to find out where, again, how high on the graph that actually is. So for e cubed, I have approximately 5.47, and for my inflection point, I have approximately 5. Okay, so my important points to include are my intercept, which again on the previous graph I discovered to be e squared before 10, but I'm going to put it on the graph just so that I can actually start my graph somewhere. I will then have e cubed as my local max, and I have e to the power of 7/2 as my inflection point. And I know that my points of interest here are at approximately 5 and 5.47. Okay, pardon the slight issue with the actual scale here. Okay, so what happens according to my first derivative analysis is that my function increases all the way up until e cubed. That happens to be at this point right here. So let me put the point down. This is going to be my local max, as I've previously discovered. And let me put the point down here. This is going to be my inflection point here, right? So I know that my function increases all the way to local max, and it increases in the concave down manner. So my function has to look something like this. It then starts decreasing, and it decreases forever on, but it now has to decrease up until the inflection point in the concave down manner, and then at the inflection point actually changes behavior and start decreasing in a more, not in a more, but rather in a concave up way. Okay, so something like this. Okay, there we go, and that is all that our analysis has revealed so far. An interesting thing to note is that the aerobic rate at the local maximum is also at the global maximum, because my function is forever decreasing from then on. And so that means that your oxygen consumption is actually peaked at approximately 21 years of age. So it's too late for me, but hopefully just in time for some of you guys to realize that you are on your way to your maximum aerobic rate.